Okay, in this video I'm going to work through the solution to the fourth question in exercises 2 of chapter 4 of the EGH 303 aerodynamics course. In the lectures we looked at questions 1 and 2 already, and question 3 is just a natural extension from what we've already done in questions 1 and 2, but question 4 requires us to do something a little bit different. So let's have a look at that question. So it says that Weissinger's approximation is the simplest example of the 2D vortex lattice method, in which the distributed vorticity along the x-axis is replaced by a single vortex of unknown strength. So if you remember, in thin aerofoil theory, what we've been doing is assuming that we've got a distribution of vorticity along the x-axis, and what we're trying to find is what that vorticity distribution looks like if we achieve the tangency condition, where we're trying to get the flow to be tangent to the mean camber line but applied on the x-axis. And when we do that, in combination with the application of the cutter condition, we end up with the fundamental equation of thin aerofoil theory, which is what we've been using for questions 1, 2 and 3. In question 4 we're actually simplifying the problem again, by saying rather than having a distribution of vorticity along the chord line of the aerofoil, we're just going to, the simplest simplification, I guess, if you like, of that is to have a single vortex, and we're going to locate this single vortex at the quarter chord point. The value of the circulation is found by satisfying the surface boundary condition at the 3/4 chord point. When this approximation is used for the flow over a thin symmetric aerofoil at an angle of attack alpha, show that the sectional CL is identical to that given by thin aerofoil theory. And if you remember, the result we got from thin aerofoil theory for a symmetrical aerofoil is that CL is equal to 2 pi alpha, giving us the famous result that the lift curve dCl by d alpha is equal to 2 pi. So can we show that? Now this, I guess the only tricky thing about this is realizing that actually the most useful way to do this is to go back to some of the content we looked at earlier in this chapter that formed the basis of exercises 1, where we look at some of these these solutions that we can put into a database for potential flow theory. So if we've got a single vortex rather than a distributed vorticity, we can approximate that just by a vortex flow field. So let's just make a sketch of what the problem is. So let's assume that we've got a coordinate system that looks like this. This is the x direction. This is the z direction. And here's our aerofoil going from 0 to C. And we're going to place a vortex at the quarter chord position, so at C/4. And what we're trying to achieve here is that at the 3/4 chord position that we achieve the flow tangency condition. So this distance here is 3C/4. Now for a symmetric aerofoil, z is equal to 0, z of x is equal to 0, so dz by dx is equal to 0, where z is the mean camber line. So in fact what we're trying to show is that at this point, at 3C/4, the flow velocity is in this direction. So v at x equals 3C/4. Now the free stream flow is v infinity. I've exaggerated this a little bit because we're going to assume that alpha is small. Is coming in at an angle of attack alpha. So what we know from potential flow theory is that if we're approximating this flow field by a single vortex located here with a uniform free stream at an angle of alpha, we can just superpose those two solutions. And we know that a vortex flow can be written in terms of the potential function. This would work whether you did it in terms of the potential function or the stream function, is equal to the circulation times theta over 2 pi, where theta is the angle measured from the location of the vortex, so measured from this point here to wherever in the flow field you're interested in. So we also know that we can work out the radial velocity when, of course, for a vortex flow we know that this is going to be 0, and that u theta, the tangential velocity, is 1 over r d phi by d theta, which is equal to the circulation over 2 pi r. So we know that the net effect of this vortex sat at x equals c upon 4 at this point here is that the radial velocity is 0. The radial velocity would be in this direction, so this is u r, and the tangential velocity u theta is going to be given by this here. And what we want is for the net flow to be horizontal, so there to be no net vertical velocity. So we need the vertical component of this uniform flow to cancel out the vertical component of this vortex flow. So let's state for flow tangency at x equals 3c over 4, what we need is that u theta at x equals 3c upon 4 to be equal to the vertical component of the free stream flow, which is v infinity sine alpha. But we can always make use of, for thin airfoil theory and for small angles of attack, small angle approximation. So for small alpha, sine alpha is approximately equal to alpha, which tells us that the circulation over 2 pi r, which is u theta, is equal to v infinity alpha. But r, so this is, remember, r is the distance radially from the vortex, so the distance r from the vortex to this position x equals 3c upon 4 is going to be c upon 2. So we can plug that into this equation and write that lambda over 2 pi c upon 2 is equal to v infinity alpha. 2's are going to cancel, so the circulation is going to be v infinity alpha pi c. Let's underline that. Now we know that the total lift generated by this airfoil with this value of circulation is rho infinity v infinity times the circulation, which in this case is going to be rho infinity v infinity squared alpha pi times the chord length. So CL, which is equal to L over a half rho infinity v infinity squared c, is going to be rho infinity v infinity squared alpha pi c all over a half rho infinity v infinity squared c. The c's will cancel, the v infinity squareds cancel, the rho infinities cancel, and what we're left with is 2 pi alpha, which is exactly the result we're looking for. So once you realise what the question is actually asking you to do, that's actually quite a straightforward problem to solve.